listed it was the heat and the radiation, but it's very hard to say that definitively. So I'm not claiming we know that was from radiation effects. Probably most of the time. And the mutant pretty much did the same thing. But it's kind of neat to see these kinds of changes. This is just one of the other colors. This is the red light. It shows the blue color going away and the organisms growing up. Eventually, we can do some spectral deconvolutions of these and extract a little more data. That's the story for now. So let me tell you in the next few minutes, since Ian said I can go on until 7:30, about what the SIMO payload, the space environment viability of organics looks like, which is this will just be a few minutes. So we looked at 4 different molecules. We looked at a polyaromatic hydrocarbon. We looked at an amino acid. And these 2 are kind of representative of what people would call prebiotic chemistry. Now, we don't know for sure that polyaromatic carbons have ever been involved in building life, but they are a great carbon source and they're very plentiful in the cosmos. So they're a potential source of carbon that, if it were further modified once it got to Earth or somewhere else, could be a starting point. Amino acids, on the other hand, we know those are useful in making life, and lots of those come in asteroids in very significant quantities in comets, even sometimes with slight chiral excess, which is another story. These 2 molecules, though, are a different category. These are biomarkers. So this is iron tetraphenylporphyrin. There's the iron in the middle. And this is anthrorufin, which is a quinone. So this is an electron transfer molecule, and this is an oxygen or carbon dioxide carrier, both. Very similar to the heme site in our blood, in red blood. So the idea is to see how long these things survive in space. So we exposed them for, actually this says 6 months, eventually we ended up exposing them for 17 months.